Okay, great. Yeah, so this one, again, like, part of calculus is, and I keep coming back to this, like, so it means like the method or something like that, the technique. And what's interesting though is that you find this in art and, writing, even though there's a technique, people have different styles of doing it, right? So you have painting as a technique, but, Van Gogh versus like an impressionist or someone else, everybody has their own sort of style that they bring. And so in calculus, there's something similar where it's the art of splitting things apart and putting them back together. But there's sort of different styles that you can do that. And, there's sort of one traditional style that's taught in classes. And that's sort of actually talking about the area under the curve. So the typical calculus thing that you'll hear is that integrals measure the area under the curve. And the reason they do that is their style is if you have a blob of stuff, you basically slice it. Oh, I guess I'll go this way. You kind of slice it into strips as you go left to right. And then the size of all the strips is the area. And so that's sort of the traditional calculus way of doing something where you sort of you go left to right and you're kind of going up and down in these little rectangles and you sort of get the total size that way. But that's just one style. You could have different styles. You could imagine taking a hole punch and punching out a bunch of circles, or maybe making a grid, or making a crisscross, or making a few different approaches. And one thing that always bothered me is that in calculus, we're sort of taught one way, or you think that's all there is, but it's really more of a point of view. So this Spark, we'll do it today, but it's really just about trying to imagine different styles to break things down. And I think you've probably had some experience with this in the previous activities, but it's really just kind of opening our brain and seeing how to approach things. And one analogy I like is it's sort of like different directors. So I've always wanted to see this where you had one movie that was directed by like 5 different directors. So the same script, but 5 different directors. So you'd have, Curious George or something as a movie. And then you have Spielberg, you have Tarantino, you have Christopher Nolan. You might have 5 different directors put their take on it. So it's the same script, it's the same dialogue, right? The same plot, but yet there would be a different kind of feeling, right? If you imagine between Spielberg and Christopher Nolan or Tarantino. So it's just sort of this idea that you might get to the same result, but the path that you took was different and it might kind of have a different vibe to it. In the actual Spark, there's a few links to different examples. So there's things like 3D printing. That is a very kind of mechanical way to print things, or the way things grow in nature, where you have crystals sort of organically evolving, or even humans building a building. Or like ants, we kind of have a certain structure. We might have a blueprint that we're following. So the idea here is to maybe take an object and ideally take 3 of it. So if it's drawing, maybe take the same drawing, make it 3 times. Or if it's Play-Doh, I'm just going to take 3 Play-Doh shapes. And what we can try to do is take 3 of the same object and try to make it in 3 different styles, but it should add up to the same amount of stuff. And see if you can be kind of creative in the way that you split it up. So in the Spark, I don't know if you have it up, but basically there's a few examples of different shapes that are kind of cut up. It might give you some inspiration about how to break things apart. But let's just take a few minutes maybe to either draw the same shape 3 times, or using Play-Doh, create the same shape, and then try to split it up in a few different ways.
Khalid, really fast for Mindy, do you want to explain what we're working on right now so she can catch up?
Oh, sure. Hi, Mindy. So for this activity, we're basically taking our building material, which might be Play-Doh. I have Play-Doh here, or it could be a drawing. And we're going to try to make the same object in a few different ways. So I had this analogy about imagine the same movie script. If you had 3 different directors directing it, how might it turn out? So for example, you have Curious George as a plot, as a movie, but then you have Christopher Nolan direct it, you have Steven Spielberg direct it, you have Quentin Tarantino direct it, you have 5 different people take a shot at kind of imagining that same script. And the idea is to sort of see how even the same result, the path that you take to get there might kind of have interesting insights. So it could be a drawing, maybe the same drawing 3 times, and just drawing in a different styles or cutting up in different ways. Or for Play-Doh, I'm going to make 3 of the same shape, and I'm going to try to split it up in different ways. And the idea is just to sort of see if the process that we get to that end result might have some insights along the way. Okay, maybe just a few more minutes. Okay. Does anyone need a little bit of extra time? Great, thanks. It looks like we might be ready, and we can kind of go through and do a quick show and tell. So we can just go around, just feel free to just give a few words about what you made and maybe what styles you tried to use. And then we'll go through and actually just analyze maybe some of the calculus implications or the calculus realizations as a result. So let's see, I guess I'll just start and then we'll just go along the top. I don't know if the order is the same in the chat, but we can call out people. So for me, I kind of made a little canoe, and I don't know if it's easy to see, but I basically made it in a few ways. So this is sort of sliced sort of through vertical slices. So I imagine taking kind of a board and sort of bending it into a U and having a bunch of U's to make this canoe. And then I kind of made like a Minecraft canoe. So it's similar, except it's sort of a cross-stitch pattern. So this is the same kind of shape, except that it's made out of a bunch of cubes. So this is sort of the canoe in the Minecraft world versus the real-world canoe, which might be made out of a single kind of U-shaped board. And then this one is sort of a 3D printed canoe, or it looks more like I guess like a taco or burrito or something. But basically, the idea is that the layers are sort of like sediment. So it's kind of going across this way. So you'd sort of put down one layer and then put down another layer and put down another layer. So for me, these are just kind of a simple shape with a few different approaches. And again, just feel free to talk about what thoughts went through your head. So for me, this is sort of my real world. Like if I were to build a canoe, I would probably take individual planks and bend them. If a Minecraft world were to build one, it would be sort of a cube canoe. And then if a robot maybe were to build one, it would be sort of a 3D printed canoe that's going sort of horizontally. Let's see. Mindy, do you want to give it a shot maybe?
Let me skip for a second. I have a little bit of background noise in here. I have to
Sure.
Okay, thanks.
No problem. Let's see. I guess maybe Shelly, if you're next.
Sure, I'll go. So I never cease to be amazed how when I start an activity and I think, I have no inspiration, I'm going to get nothing out of this, and then I actually have some cool insights.
Awesome.
So I was trying to make a circle or a half of a circle in the case of the one I'm about to hold up. So I went with the boring, I'll just start with discs because my brain just wasn't on yet, It's not much of a circle. But it was funny because I was trying to get the second and the third piece. And I had one of those duh moments of like, well, you have to use less Play-Doh to make a smaller piece.
Yep.
But I thought, oh, wow, though, for kids to understand the concept of area, which is actually pretty hard for my kids to grasp, that to do it with Play-Doh, like you need less Play-Doh. There's less Play-Doh in that next piece.
Exactly.
So that was my little aha of the ugly little circle. But then I made a circle out of circles, which I thought would be
that's cool.
the least likely to look like a circle, and it's actually my best circle.
Wow.
Or sphere, I should say.
Yep.
And then I did the typical Play-Doh roll into a snake and tried to make one. And
nice.
my insight there was you need a thin one, but you also don't get a true sphere with a snake very well. It's a little harder because you need a really long piece if you're going to go all the way around, and then you're essentially just recreating this. So a solid piece. So if you're going to just wrap around the outside, it's going to be hollow. So just some fun things that popped into my head. I don't know how calculus they are, but that's what I...
Oh, no, that's great. Well, and what you're realizing is that certain approaches might be kind of subsets, or this is so nerdy, but certain approaches are sort of turn into other approaches. So like if you have eventually it'll look very similar to the way that the other one works. So it ends up being kind of a special case and a more general case of the same approach. Yeah, that's awesome. Let's see. maybe, is it Eogrin or?
Okay, they can hear us now. It's Emily. Okay, so I ended up with very boring hearts because we had a cookie cutter. So this one I sliced.
And I'll show you
This one we tried wedges, or I tried wedges. That one's falling apart.
Oh, awesome.
And this one was a more, let's see, complicated wedges with
Oh
an
yeah.
outline, like a puzzle. We were thinking about puzzles where you get the outer edges and then you get the middle. And then I made one out of little balls too.
And here's mine.
And
Oh, it's awesome.
this is a stack of hearts actually, which is interesting. Okay, Nora, you want to show yours?
Yeah.
Okay, just put it so they can see it.
This is divided up into diamonds. This is like a circle.
It's a circle divided into diamonds.
Oh, cool. Awesome.
Okay, what was your other ones?
And then I have this one. It's kind of like this fractally thing. It's like there was an X in the middle, and then there were two prongs reaching off of that.
Yeah, here's some of the squares. That was a good one.
Here's another one.
This one is kind of in squares, right?
Yeah.
Which is interesting with circles, but then we were talking about how that works with the fuse beads too, right? The fuse beads were in a circle, but they're not circle. Well, they actually are little circles, but they melt squares, sort of.
Okay. And then there's this one, which is kind of hard to understand.
It has triangles in the middle.
I like that, the triangles, and then it sort of goes out. Yeah, so that's sort of an inside out or an outside in kind of crystal approach almost. Yeah.
Yeah, that's true. And then one more here. This one is actually similar, only with a bigger border.
Yeah, it's a little bit more round and it's got the kind of curve. That's great.
And then Anna here, let's show them this one.
Here's my stack of hearts.
So here's your stack of hearts, yes. So Anna started with an egg shape. Let's see if I can show this thing. And she started cutting it into wedges, but we were talking about fractals the other day, so she started cutting each wedge into smaller wedges.
Great.
Right. 5 wedges and then 5 wedges each. So that was kind of interesting.
Awesome.
So that's what we got.
Oh,
Oh, okay, one more.
No, I have
Oh, 2 more, I'm sorry. Okay, and this is another egg shape with a different design. It's got like a, yeah, that one's kind of complicated actually. And one last one where we cut the square in the middle and then the designs on the outside. Okay, I think that's all it was. Okay.
Awesome. And actually this brings me to a nice kind of realization too, is that with calculus, so we have these cool shapes and we're able to show, on a screen share what we're doing. But then the question becomes, okay, imagine, you're in the 1800s and you're writing letters to your other calculus coworkers and you're trying to describe what you're doing. And you might be able to draw a diagram, but ideally you're giving them instructions on what to do. So you start to realize, wow, like some of these shapes, like mine are fairly simple, but those ones, like the fractals, are really intricate. And so now there's this challenge, and this happens in music, it happens in language, with art, with anything really, is, okay, I have this very rich idea that I want to create, and I have to sort of distill it down into something that's communicable. And it's really, and that's actually one of the challenges. So we create words and symbols and things to try to describe it. But there's a lot of shapes. Like I was just thinking some of those shapes, I don't even know, like my calculus skill, I couldn't describe it. I have to say, this picture is the best that I could do to describe that, which is great because there's a richness beyond what, like in most classes will teach you ways that are very linear and kind of very easy to describe, but then you might have a new technique which is not easy to describe, but it could be really interesting. And so that's sort of one of the challenges. And we'll get into some of the terminology after too. Great, thank you. I guess Randy, do you want to give it a shot?
Sure. So I just made a boring triangle out of paper. So let me just turn this down here. So the first one was just a triangle made out of triangles. And I can sort of see that there.
Nice. And are Are they all the same size?
They're all the same size. So I actually made this by, all of the pieces are 8 pieces. And so this was made first by, first cutting it in half. Hold on, here we go. First cutting it in half, and then taking that half and cutting that in half, and taking that half and cutting that in half for all of them. And then the other shape was a triangle cut out of, let's try that. Triangle cut out of, really sort of like rays, but going to the midpoint of the shortest side and cutting half and cutting through there, and then going through the midpoint of that next side and cutting through, and then going to the midpoint again, cutting. And so that made a very different design, and it was really hard to cut with it getting so tiny, narrow.
Yeah.
At the very ends. And then the last one was just the normal
Kind of vertical.
just cutting in bars. And to get this even, I just folded to get the even line. But those were the 3 things that I did then.
Great. And actually, one thing I'm noticing is I think the area of each of those triangles in that second one would actually be the same. Just kind of a neat, because if it's the same base and the same height, so even though the angle is a little bit different, the actual amount of paper for each of those triangles would actually be the same, which is sort of a neat kind of side effect, I think.
Which?
So the second example you showed with like the rays.
Oh, this one.
Yeah, so basically they each, I think as long as the width on the bottom was the same, so the height of each triangle is essentially the distance that it goes from the top to the bottom, even though it's being kind of skewed, it would actually be the same area each time. So it's kind of a neat, and that's like, it's like, whoa, wait a minute, because it's the same, the bottom part is the same, and it's going to the same top. It's just that it's sort of being, slid a little bit. But you can imagine if it was made out of putty, it's the same amount of putty, and you're just kind of stretching it.
Yeah.
Bit. So that's kind of a neat, like, whoa, okay. That just happened to be a nice coincidence there.
I hadn't even thought of that. That is pretty cool. Yeah.
But my brain is arguing with you, even though I know you're right.
It's hard. No, it's true. It's a good, like, and that's actually, and you want that tension, that creative tension. I had to, when I'm looking at it, wait a minute, look at a formula says 1/2 base times height, but wait, it's being skewed. But the height is actually just if you drop down the top of it to the paper, and as long as they go. So yeah, when you're explaining it, it's not like these kind of things are just jumping out at you automatically. You have to kind of say, wait, like they kind of look the same. It looks roughly the same. And actually a fun thing would be, okay, now that we know calculus, here's the fun one. What's kind of a calculus-y way to see if it really is? So pretend you don't know the formula. And let's say, okay, like, your kid makes these triangles. And they say, okay, are these the same size? Like, can you think of a few ways that we could maybe figure it out? And this is, I'm just, spitballing. I have a few ideas, but just like if somebody said, are these 2 things, like let's say the first one and the last one, so they look really different.
Yeah.
Exactly. And it's like if someone said, well, are these the same size? What could you do? Yep. Can you stack them on top? Although maybe cut them.
I'd cut them in little pieces and lay it on top of another triangle and be like, even though I had to move them around, look, it's the same amount or something like that.
Exactly. Yep.
Because I don't know the formulas.
And you don't need to, and that's the thing. It's like the formula is one technique, and it's a kind of a shortcut. But exactly, stack it on top. Or I was even thinking I would take Play-Doh, cover on both, and see if the same amount of Play-Doh could cover both triangles, basically. Like put one, and then if there's any extra, then I know. So that's exactly. It's like, wait a minute, we're trying to measure things, but maybe there's a clever way we can sort of, rearrange something. And so, or maybe you make it out of Play-Doh and you sort of try to bend it. So you start with the first one and you just try to bend it and see if it makes the second one. Although Play-Doh, you can kind of cheat because you can squish it and get it thinner. But the general idea is that if it's the same thickness, you might be able to make it. And that's it. And that's kind of the calculus intuition is that, wait, maybe there's a way to kind of move these things around. Um, awesome. Yeah, it's just a spark within a spark. I love it. So yeah, so I think hopefully the general idea is that once you start looking at how to break things apart, the calculus mindset, and again, I know I love analogies, but it's basically, you can see algebra. I see algebra as a description of a result. So it's kind of like, here's a cookie. Here's a chocolate chip cookie. You know, it weighs this much. It's got this flavor, you know, this much sugar, whatever was put into it. And algebra is sort of a description of what you have. So the Pythagorean theorem, or, you know, a circle or something, is kind of like a static description. And then calculus is kind of a description of how you got there. So if algebra is the cookie, calculus is the recipe. And so it gives you a little bit more understanding about what happened. And it is a little bit more work, because if you have the recipe and you want to get the cookie back, you have to follow it. You have to kind of complete the recipe, and then you get the final result. But the neat thing is you sort of know how it was made, and you might know some nuances that weren't there the first time. So like in this case, I have these kind of boat shapes. So they're all the same boat, but I follow different recipes to build them. And so as a result, I might know something different. So for example, this Minecraft boat, if you were making a boat out of Minecraft blocks, you would probably know exactly how many blocks you used, because it's so easy to count. But if you made it out of kind of squiggles, then the squiggles are a little bit more difficult. So the idea is sort of knowing how you put something together, you get that extra level of depth. And that's sort of why calculus is used all over science. It's mainly because you can use algebra to describe things, but you're not really explaining how it happened. And in science and engineering, you sort of want to know the how. You want to know the details, not just the cookie. You sort of want the recipe so you can tweak it and change it. And so it's hard to change a cookie, right? Like if you have a raisin cookie and you want it to be a peanut butter cookie, you really, like, you can't swap out the raisins for peanut butter in the cookie. The easier thing to do is swap out the recipe and then remake the recipe. And so that's sort of the calculus technique, which is that, you know, if you want to change something around, go to the recipe, change the recipe, and then remake it. And that's much easier than trying to change the final result. So in science and engineering, that's why calculus is so useful, because you're kind of giving people the recipe and not just the final endpoint. So that's sort of like a high level kind of intuition. I'm just trying to take a look at some more notes I was taking. And the other thing with calculus too is that we're sort of comparing and contrasting different approaches. And calculus gives us a kind of qualitative and quantitative way to describe it. So I can say, oh, this approach has fewer pieces than this. So this is the Minecraft boat, and it has a bunch of little cubes. And this is the human boat that was made by kind of U-shaped things. And so I can say, you know, qualitatively, oh, the Minecraft boat has more pieces because they're smaller. And then quantitatively, you could even have a formula that says how many more pieces it has compared to the other. And so there's sort of that transition from that kind of qualitative description to being really, really specific about, oh, I know exactly how many pieces were here, or I know it uses 5 times as many as this other one, or the pieces are such and such size. But it's really about getting that language to be sharpened up. Let's see if there's any more little things. And also another thing too is even the pieces. I think people were noticing sometimes when you build it, sometimes it's actually easy to make self-similar pieces. So sort of that idea of taking a triangle and splitting it into triangles. And so Randy, when he did it, he had a big triangle, cut in half, and cut those pieces in half, and if you do it in a way that's self-similar, like you're making smaller triangles, it's really easy to see, oh, they're all identical, and I can kind of measure them and count them up, versus when you're cutting in different ways each time, now it's a little bit more work maybe to measure them. So the circle that was being made out of smaller circles and so on, you sort of, there's kind of a symmetry that happens, which if you decide to cut it that way, things become a little bit easier to compute. So yeah, those are sort of, I guess, the high level intuitions behind some of the things. And it's really just about to train your brain. So just, yeah, I love that Randy had that thing because we could measure it. And that's just, again, the general purpose. If you have a shape that's a weird, curving thing, you can put the Play-Doh on it, take it off and put it into a square and see how much that would be in a more easy to measure way. Great. So those are sort of like the high level questions. I'm not sure if there's any kind of maybe general calculus questions or maybe teaching or kind of interactive questions that you'd like to go through. Basically, we're planning on for the future courses to have similar activities, but also maybe have more bridges into some of the more formal descriptions for people that are maybe a little bit older that can use those things. So for example, the area under the curve, there's a little bit more formalization that can be done and using the proper words. But the idea really is to get that intuition and, be able to, in the Plato world, make things happen and then eventually sharpen that up into the calculus world. Oh, sorry, did everyone get a chance? Oh, sorry, yeah, Mindy and Holly, I don't think we got a chance to see your shapes yet.
Unmute. Yeah, I actually, because I came in a little bit late, I did it with different materials, and then I realized maybe I'd done it wrong, but I don't know. So at first I did, with clay, I made a bunch of grapes, and then I used different materials, so I used some pipe cleaners and twisted them together in groups of 3, and the different colors are each group of 3, so there are 12.
Is this
And then this is beads. I was going to string it together, but it was faster to just use the pipe cleaner. And then I realized that maybe I needed to try to cut it up differently. So I was playing as you were talking, and I made another bunch of grapes with straight kind of rods, and I attached the rods together to form the grape shapes. So if I had more time, I would have perfected it a little bit better, but and then this one, and if I kept going, I would have made a bunch of grapes with discs. So these are all, I don't know if you can see that. Sorry, I'm kind of far away. But they're like little discs that are attached together. This is it almost looks like a bunch of bananas, but they're the rods together. And then that's the original bunch of grapes with the balls.
Awesome. And did you find some shapes easier to make than others? Was it harder to get the rods to behave compared to the other shapes? Yeah.
Yeah, it was definitely. And breaking them off and then trying to imagine, well, I have to squish these together to make them round at the end because here they are pointy now because I've kind of broken it apart. So yeah.
Awesome. Yeah, and that's the thing too. There's this sort of, in the mathematical world, it's nice to be able to make it. But then you realize in the real world, if you have these constraints, like it's a rod and it's going to be pointy, that's sort of that transition. But it's nice to have those trade-offs available that you can make. And then, bye. And let's see.
Hey, I had a question. So I looked at soccer and I lost my actual soccer ball. The kids. But that was really quick. I just looked at a soccer ball, and I think other people have done circles before, but imagine it's a sphere and not two-dimensional like this.
Yep.
But then after I did that, I had some more time, and I was I'm not sure if this at all translates, but I was looking at the game itself through my 3 different kids and what their definition would be if I asked them some specific attributes, like what soccer, how many people should be on each team, optimizing for what's fun for them. So in their world of a successful game of soccer, and I had some specific attributes. How many people, how many players would there be? How long would it be? What's the attitude, the general energy on the thing? And I had different kind of a little, table.
Yeah.
But since it's not a shape, I'm trying to see if I could somehow, how do I translate this into calculus?
Oh, no, good question. So I think soccer, there's from the way that the players are in the field, maybe. So, I don't know if this is, this might be more quantitative, but for soccer positions, they have different, it's 5, 4, 5.
Yes, exactly. Formations or whatever. Yeah.
Formations, exactly. So some formations are kind of so an even formation where you get the same, so is it 11 players in the field? I forget. Maybe it's 10 or 11, but if you had an even number of players, 3, 3, 3 and a goalie, let's say, if you had that would be sort of the wedges because it's the same amount each time. But if you had 2, 3, 4 or, 3, 4, 5, let's say, that's kind of the rings that are getting bigger as you go. And then you might have one that gets smaller, or you might have 3, 5, 3 or something where it's bigger and then it's smaller again. And that would be sort of the boards, if you're cutting horizontally, where the boards start small, get big and go small again. And so there's a sort of quality, and that's actually quantitative because you can actually measure the difference there. But you see that slicing strategy, like the metaphor of a slice, it isn't just a shape. It can be a strategy where, on a soccer field, do you want more offense or defense?
That's good.
Are you kind of leaning more towards the front? And even in a game, how about your energy level? Are you going to tell the kids, hey kids, play your hardest the whole way through, or play the same level the whole way through, or maybe save your energy for the end, or maybe be strong in the beginning and then sort of, Peter, so like when you're racing, you know, do you pace yourself evenly, or do you kind of put your energy in the front or the end? And that's sort of that idea of just trading off whatever it is, energy, the strategy. You know, how fun is it? Is the game equally fun the whole game? Or is it more fun in the beginning and it gets less fun, or it gets more fun? You know, so that's sort of that general idea that, hey, this static thing, I can break it apart in a lot of different ways. And yeah, I can describe it quantitatively, but I can also qualitatively look at it as well. Yeah.
Oh, that's great. Thanks.
Yeah, for sure. Let's see. Oh yeah, for chemistry. Yep, exactly. Yeah, there's that soccer ball. I don't know. Have you seen that Buckyball? So they've made like a soccer ball out of atoms. It's sort of like a wire frame, and they've made like a little tiny. It's like a microscopic soccer ball. It's really cool. Yeah.
So cool.
Yeah, Randy just said, yeah, C60 I guess is the fun
Okay.
But yeah, that's exactly. I mean, the point of these sparks and things is really just to. I don't. For me, it never. I've enjoyed math, but I didn't like it because I was trying to look at a license plate and add up all the numbers or something. It was more like, oh, like that's just kind of neat. Like, what if, or I wonder if, and usually those kind of I wonder questions, they're loose or qualitative. And then eventually, if you're really curious, you might try to sharpen it up. But oftentimes just having that interest is enough to kind of put you on that path of just wanting to explore more. Yeah.
Cool.
Yeah. I'm just taking a look here at Holly's question. Questioning process would be, I see. Yeah. So the questioning process, I think that's one thing we'll probably want to add into the next round, is basically kind of more examples. So I feel like we had the sparks here, but we didn't necessarily have enough hand holding in terms of like, okay, here's like what it might look like. So now that we've done these, we'll hopefully have pictures and videos of like how people did it and even things like this. So yeah, it's a little bit tricky, especially if you've never done it before, to know how to lead it. I'd say the general thing though is just that I'd say again in calculus, it means, the technique. So it's this viewpoint of breaking things apart, putting them together, and having a few different ways to do it. And you just try, like a circle, a soccer game, anything. You try to look at it a few different ways. It's kind of this artistic eye, and you have different perspectives on it. And then sometimes you can get these little insights where, these triangles are the same, or maybe they're not the same. How do we find out? And we'd like to maybe add more kind of hand-holding guidance there too.
Khalid, I was going to throw in there too. There's 3 questions that, regardless of the spark or the class or the whatever, have really helped me. So they're very general. They are, I noticed. So like, I'll go back to my example. I noticed that I used more Play-Doh, or if I kept pulling the same amount off, I couldn't make smaller pieces. So when you use with your kids, what do you notice? They're just training themselves to look and observe. So Khalid noticed that all those triangles should probably have the same area. And then the next question is, I wonder if they really do. And then his brain was like, well, they have the same base, they have the same height, they have to be. So that's when things start sparking and turning into the fire, is when you go from, I noticed this, I wonder if that means, like Mindy, I noticed I can break apart a soccer game. I wonder where the math is. I'm going to ask somebody. And then I wonder if I can make it this way. And then another great question that Maria always asks in natural math is, what if we do this? What will happen if? So I tried this. I wonder if we can do this to it. What will happen? What do you think they will be the same size? If I cut all those little triangles up and I weigh them, will they all weigh the same amount on our kitchen scale? And kids, honestly, I was kind of, when I started, I was like, I need a kid. They're more creative in coming up with weird, well, what if we chop it into these pieces? And they'll actually kind of lead me along better. But I notice, I wonder, and then what would happen if, are 3 really, really powerful ways to help get your kids talking, because they notice things you don't. And then a lot of these sparks grew out of those kinds of questions ourselves that we asked ourselves. Hey, I noticed that if you do this, hey, that's a spark. And then things came from there. So hopefully that helps too.
Oh, that's great. Yeah. And I think it's really this kind of attitude of exploration. So it's not about, we're trained in math to have these very definite endpoints and things, but it really is just about opening up to exploration so you can find and discover things for yourself.
So I'm going to hop in then at the end here and ask for your feedback, beg for your feedback. This is the first time we've taught this class as a two-day workshop and then a big gap in another one. So any feedback you have on, oh, that was great, or that was too long, or you only really need one and then another, whatever feedback you might have, troubles, and you don't have to give it all right this instant. You're welcome to email myself or Maria or Khalid or anybody, but any feedback you do have, good, bad, ugly, we will take it all.
And I noticed, I mean, for me, I don't have any kids, so I have the easy part where I'm just, giving out the homework, so to speak, and then people have to, or not have to, but they get to work on it. But I realize there's sort of, it's difficult sometimes to make time or to kind of do things. So we want you to be successful with it. It doesn't, like for example, there's a lot of like online courses out there, like 12-week MOOCs and things like that. And I've tried to sign up for them, but then I just lose steam and it's hard to plow through it for 12 weeks in a row. So I realized, I like to do things that would be successful for me, or I want to do things in a way that would work for me as well. So to say, okay, what would actually work for me? So having in-person things, or having, is it better to have 2 days in a row, 3 days in a row where I can just dedicate and then I know I finished it, versus an obligation that I feel to do something. So, things that actually help motivate you, or things that seem to be easy to complete. We'd love to know what worked for you.
Yep. And another thing that will happen this summer probably is that we've had a lot of people asking for, will you do this with our kids? And then we'll sit in the background, which is what I do in my other company. And so we'll probably be offering calculus for kids, where it will be these sparks, but your child will be the front and center on the camera, and we'll be playing. And I, and possibly Khalid, I haven't asked him yet actually, we'll be guiding it through so that you're just the fly on the wall watching him and I talk it through with kids, and your child's playing, and then there's less homework, but you get that benefit. So that's something. Summer camps are kind of fun, and online's nice. You don't have to drive anywhere. So that may happen. And if it's something you're like, ooh, I'd love to see that for my child, and I'd love to see that, especially like Randy with the older ones, where Khalid's a lot better at tying it to the formal math and giving them a great foundation before they take calculus in high school kind of thing. That's some of the ideas that we have, but we don't know what you guys want for sure. So anyway. Oh, in the chat box, did you see that from Holly, Khalid? I noticed, I wonder what would happen. Oh, good. And no, Randy, there's no end time to the forum. You get to be in there forever. So if we make a new spark, you'll get it. If you want a spark, like you see a great, we would actually love it if you're like, that would make a good spark. Send it our way and we'll turn it into something.
Yeah.
Okay, cool, fantastic. Thanks.
Then you can just throw it in the form and be like, hey, I was doing this with my kid and I think this would make a good spark. If you want to make the spark, we'll let you, but if you don't, we'll make the spark. So anyway, are there any other questions logistically or anything?
No, I think it's good that you're asking for feedback. Maybe we could talk about it now.
Go ahead. Yes, we would love anything you have right now. Go ahead.
I love the 2 days in a row format in the beginning. Things just didn't kind of get lost. It didn't feel like there was a lot of pressure first. I thought, there's going to be a lot of pressure, but I'll just do what we can do. We'll do something. We'll do nothing. And it was nice to have that consistency. I thought that it was intimidating at first to think about it, but in practice, it was really useful. And then with the gap, I could have used a little bit more push information. Like going to the portal is good in theory, but more emails or more just like a quick worksheet or a quick question. Ask your kids this today. Even just
I totally hear you.
I noticed and I wonder, use that today or whatever, something like that, a little bit more pushing. And then in the reminders, I don't think you can over remind. I would remind. I noticed you sent the email notification out for this 4 days ago, but I was expecting like another one yesterday or something like that. Just to kind of have it really up in front or in my inbox so we don't.
You want us to be more annoying. Got it. No,
more annoying. Yeah.
But I know everything gets lost in your life.
Everything gets lost because everything else is so annoying. There's always other notifications.
That's actually what my problem was.
Everything's so notifying. I hate it all, but like it's kind of the most annoying thing gets the attention.
No.
2 emails in a week is not too much. Like 2
Okay.
in a day is too much, but not 2 in a week.
Okay, well, that's good to know numbers. We're math people. No, I'm teasing, but I like the idea of pushing more. We haven't really done that, and we have the forum there, but I'm with you. I'm really bad about going to forums myself. I actually felt guilty. I'm like, oh, I haven't been in there, and I'm supposed to be helping moderate that thing. So, and I think it's great. We can send you a spark, and you can totally ignore it, but at least it sparks the idea that you might want to do something this week.
That'd be great.
Okay, that's great feedback. Thank you.
Sure.
Anyone else have anything that they on their head right now you want to share?
It was a little confusing finding the sparks at first. So some of the items in the forum had sparks with them, and some of them didn't. It seemed so. It just.
I would like to, Len, maybe Mindy, you can weigh in on it too. I thought they're PDFs. We can put them all together and at the beginning of the course give you all of them.
Yeah, that might be easier.
Would that be easier? I know then it doesn't remind you, Mindy, so then maybe the emails become, hey, have you tried this today, rather than an spark kind of.
Both.
Here's the spark in case you don't remember where you downloaded the file, because that's never happened to anyone else but me, right? So sending out all of them in a PDF format. I had thought of that actually, because they're a little confusing to find, and you have to know that you need to log into the forum. So
yeah, that's easier.
Anything else, Randy or Holly or Sunshine?
I felt like the age on this for what this specifically was really more geared maybe to cut the age down on like this specific kind of form or sparks, and then for the older ones really have some way of really tying more directly in more of the actual math and terms and equations. Even if it's not necessarily I mean, so some of the stuff is like really pretty simple in terms of like the basic ideas of the formulas for derivatives or things like that wouldn't it has more meat and really gets into the actual calculus without being so completely overwhelming to somebody that's new to it still.
Yeah, I think that's one thing too, is like what age range are we trying to go for? And there's probably one that, or I don't know if it's a different set of activities, but something that's more geared for middle school, high school kids that are, someone who's doing a science project where they actually do want maybe some more of those kind of tangible quantitative things, having an age specific or age targeted activity, I think would be good for them. Yeah.
I know that this course is it's like for kids 5 to 12, but I don't know that was written very clearly really anywhere in particular. Like when it was created in discussion, when Maria talks about it, it's like teaching kids calculus between the ages of 5 and 12. So that's kind of what you're sensing. And I'm also thinking Khalid has a site Better Explained. That's a much more of what you're talking about, like the metaphorical and going to, here's what it looks like in calculus. We're not doing tons with it, but this is what it looks like. His is kind of that bridge between where we are now and there. And so that's a great site to check out too.
Yeah, I want to jump in on the age discussion. I think there's a really good opportunity there around like middle school or late elementary that's totally missing. Khalid's site is awesome, but there's no bridge there that gets from like the really cool Play-Doh visual activities to the formulas. And I found that the things that I got out of this from the workshop really applied well to my 4-year-old and my 6, 7-year-old. This perfect level for them, but my like 9, 10-year-old, it's like 5 minutes and he's on to something else, and he's really into math, and so I was really struggling to try to make that connection for him into the formulas, and couldn't do it. Even though I have a strong math background myself, it's just also theoretical. That there's a really good opportunity in there, somewhere around the 10 to 15-year-olds, like. Or some
it's sort of like pre-high school, but kind of late elementary, middle school. I think there's a point at which you do need to start, or need to, but I think the kids would appreciate making it actually more quantifiable.
Yes.
So right now I think the sparks originally were intended for 5, 6-year-olds, so maybe they don't quite know counting or arithmetic, like blobs and bigger than, less than. But then at some point, once it's not, it's kind of it's a little too, not vague, but it's probably a little bit too not specific enough for those kids that do have mastery of counting and things like that, of course. So you can sort of measure things. Yeah, that's really good feedback.
I think too, they still are great sparks if you think about the word for even the older kids, because I as an adult still learn. It's just asking for the more, like it would be really cool if there was like part A spark and part B, taking Randy's, slice that triangle. Now, okay, you don't know the formula yet. How are you going to figure it out? And again, that doesn't require any counting. Your 5-year-old can do it too. But then saying, well, let's see, can we try to come up with a formula from these parts? Yeah. And then the next question is guiding it to look like math for those kids. Yeah. And if you know calculus, you're going to guide your child differently than I don't. I don't have the formal training that others do. So I'm going to guide mine a different way. And for me, it doesn't matter what you put on the spark. We're not going to get it on the bridge of the math and calculus because I don't know it. So sometimes it's my own, that connection, that level, the part that for me is hard is I don't have it. So when I'm sitting with Maria or Khalid, my kids would get far more than they're going to get out of me. And so if you have the math background to bring to that type of spark, you're going to be able to really launch. But you can hand that to me and it's still not going to bridge. Does that make sense? So that's, I think, my feedback to myself and as well as you still have, when you get to that point, you have to know the math yourself. And we're actually looking at kind of somehow tagging things like this for like, how much math do you need to know to guide this experience? And so I think that's part of why they are like this, is because you don't need to know a calculus to do this. But once we get to those kinds of sparks, you do kind of have to understand what in the world it is to guide the discussion and help your child and make the bridge. Otherwise, you're going to need a teacher to do it. So like in your cases, you can totally do that. Those sparks will be really useful to you. So it's in the works. I think it's coming.
Yeah. Actually, it reminds me a little bit of like language fluency. So they have different like fluency. I don't know, like the CIA and things, they have like the 5 levels from like, you get hand signals to like, writing literature, like French literature or something. And they basically have these levels where, like, what does it mean to be fluent in English? And there's like, okay, I can go to a shop and I can order a cheeseburger. Okay. And then I can write down that I can order a cheeseburger. And then I can like have an essay about a cheeseburger, or I can like write a treatise on it. And so in math, it's sort of similar, where right now we're sort of in the go to the shop, describe what you want, and the shopkeeper sort of understands what you want to get. And then eventually there's like the writing down the symbols and maybe even analyzing the works of others. So I think there is that bridge that's needed, where it's like, how fluent do you want to be? But there's like written fluency, spoken fluency, kind of compare contrast. And so, yeah, right now we're definitely at that sort of, I can communicate, but it's not necessarily like in the formal sense. And we would like to get people, as far as they want to go on that path, to at least have a guide there. Yeah.
Thank you. Is there any other feedback that you have on the format of the class, or any other problems you ran into, or just if you have any great spark ideas?
Somewhere along the line, I missed the duration of how long these videos are, and I thought it was an hour, and it's more like an hour and a half, and maybe that was just my I missed it somewhere, right?
Yeah, that's I don't know if we had a hard stop. Usually it's meant to be about an hour, but then I wonder if maybe we might want to have a more set, not agenda, but just kind of, okay, we'll do the activity for like, for the first hour, and then maybe have 10 minutes for questions. They tend to go for about 90 minutes, even though 60 is probably what we have material for, I guess.
Yeah. Okay. Then that would be even just that information, like budget an hour and a half, so I know what do I need to set my kids up for? Because we all have kids.
How long does the movie need to run?
How much childcare exactly? Otherwise, they can't be fully present because I'm also doing childcare.
Yeah, we don't want people.
Is necessary, because otherwise you won't get people for the duration.
But with that said, feedback wise, like, we'd love to know if 90 minutes is too long, like if you're kind of worn out by then, or especially, and with kids, we don't go that long because they're just wiped out. I know when I teach classes online with children, the younger ones, we go about 45 minutes, and the older ones, we can go about an hour. If we go less than an hour, they don't get enough play. I feel like I have to interrupt their activity. So, there's a lot of just quiet time in this class where you feel when you first teach them, you're like, it's really quiet, but people are doing things, but you don't want to take too long on it. And so, I don't know that it was actually clearly said. And I've been in a class where I thought it was an hour and it was an hour and a half too. So I know that feeling. We'll add it to our course descriptions of we need to start stop times so people know. Yeah, it's a big issue. So thank you. All right. I've recorded all your feedback so I don't have to try to remember it. Yeah, Sunshine, I can give you a link to my family math class. It's actually just here. This is my website where I'm a homeschooler and I teach classes in all subjects, but I teach math directly to children based on natural math principles. And I do a family math class. Right now it's during the day. And I'm talking with Maria about doing family math in the evening. So again, if that's something that you're interested in, we don't want to do it if there's no one that wants to do it, but we've had a little bit of interest like, oh, I'd love to do that, but my kids are at school. I want to do it in the evening with them. And we just play with math. And I pick subjects that kind of hit the holidays or whatever. And there's not a rigid structure. It's a math circle online. That's basically what it is. So anyway, you were homeschooled too at your house, Randy? Yay! That's cool. And Mindy too, not surprised.
So one thing that I had realized with the triangles here, as you were talking about it, was rather than even just talking about like the first one and the last one, those seemed really sort of hard to try to cut up. But if you even just look at just these two, it's not immediately obvious that on that first cut that you actually have two things that are exactly halves.
Right.
And those shapes are, I mean, if you try to use Play-Doh with these two, you could convince yourself either way that either they are or that they aren't. But with something larger like this, it's just as valid an experiment.
Yeah, it's a great thing. And so it kind of gets to this interesting, I mean, for me, like these are the realizations I'm having like right now. The only important thing about the size of the triangle is really just the size of the base. If they're all the same height, so you can imagine the kind of a clothesline at the top, so all the triangles are going to the same clothesline, it's really just how long that shadow is on the ground. And that's all that matters really. So it's pretty neat. Yeah.
Yeah.
And my brain is sitting here trying to remember geometry and how you figure out the area of a triangle when it doesn't have a 90-degree angle or if it matters. And that's what I would be doing with my kids. Because we can figure out a 90-degree angle because it's half of a rectangle.
Exactly.
But where's the height on the other one? Where's the line? What am I measuring?
Well,
Exactly.
on this one, it helps you because you already had a 90-degree triangle previously, and then you cut it. So the height is still, the projection over. So,
right, but if I'm trying to prove they both have the same area mathematically, what do I measure for the height on a scaling triangle? And that's what I'm trying to remember. I know someone else already figured it out. But the joy with your kids is being like, how are we going to do that?
Right.
And I actually really like being dumb about it because then my kids are like, well, let's try this. And if I really don't know, then I really get out of the way of their math.
Yeah. No, it's a great, and in this case too, one thing you can do is you can sort of treat the triangle as being half of a parallelogram. It's kind of, now we're getting a little bit, so like the really skew triangle, if you had two of them, you could imagine a parallelogram that was kind of like, I don't know if I'll try to draw it here. So it's sort of,
but this is what you'd be doing with, like Mindy was saying, like my 10, 11, 12, 13, 14-year-olds. This is when it gets cool for them.
exactly.
Hey, just flip them over, Randy. Put the skinny ends by the fat ends, every other one, and see if we end up with our parallelogram.
Oh, and you can even take the pieces too. Exactly. So a parallelogram is kind of a rectangle, but it's been kind of squished. And so then you can take that parallelogram and try to unsquish it back into a rectangle. So you can, through a series of steps, realize that there still is a rectangle there.
Oh, but look, he's making exactly the same. Now they're just squares and your brain can go, yes, they all have the same area. I don't even need a math formula anymore. That's easier to visualize. That's really cool.
Yeah.
Kind of, and this one is
Longer.
skinnier than this one, so.
But it's skinnier.
My brain's not convinced that they're the same, but it kind of works out.
Yeah, you'd still like to, But you're getting closer to making them more regular, and that's
Right.
sort of the approach where you're saying, okay, this really skew shape, can I rearrange it into something that I know is really easy to see? Yeah. The thing is with humans too, we don't like taking angle, like something that's kind of off kilter. We look at it and we don't really like to think of cutting it in half. We just, naturally have to put things in kind of order. So it's kind of fun to feeling that creative tension that actually I like that tension because it means my brain is learning something, right? It's like when you work out, the pain means that you're growing. So here it's like, okay, this little confusion means that I'm learning something. So that's good.
Those lead to really good bridges to other things though, like Randy brought up calculus, but that brings up psychology. Why does our brain not like angles? Why do we want to chunk it up? Why are we drawn to perpendicular things? And so if you have a child who doesn't love math,
Yeah.
those questions will bridge to other things like what I think that's really interesting. Why doesn't our brain like that? That's really psychology, not math or learning. But you've brought the math to the things they do like and the questions they do ask. And so math then doesn't become this other thing over there. So kind of
Exactly. Yeah. It's just another field that you can relate to things.
That's really cool.
The other thing that really struck me was these were both the same size triangles when I started. So that also means that this triangle, half,
that's awesome.
and it's the same as that.
That's amazing. So each of those is 1/16 or something, right? Yeah. Or they're 1/8 of the total. That's
Right.
amazing. And you would never look at those and say, oh, they're the same. Like this is where math, it's like, oh, if A leads to B and B leads to C, so like you can through deduction figure out those are the same size. Which is amazing. That's really cool. Yeah.
But having that understanding intuitively of what area means and that's a really great skill to have of these are the same size to overcome. Like my trouble with physics is overcoming your natural reaction to what's really happening.
Right. Yeah. You have to sort of, I think it's okay to have a natural reaction. It's just training it. It's sort of like, people are scared of maybe like spiders or something. It's like, oh no, but maybe some spiders are okay. Or spiders is maybe not a good example, but dogs. A lot of people are frightened of animals, but then you realize, oh, okay, that natural, it's not a wolf, it's a dog. And that natural aversion might be overcome. Yeah.
So, all right. Well, thank you for hanging out. Thank you for your feedback. Thank you for your awesome shapes. Thank you for sharing and coming. Spread the word. We're going to teach it again in March. And Sunshine had asked, you're welcome to come again. I think we'll probably use the same sparks because we get better when we use the same sparks over and over again. Yeah. So, but we will be teaching it again in March. And then I think it'll go to every other month. And we'll just make sure you're on the email list and you'll hear about all the other stuff happening in the coming months. So excited. Holly, for calculus, there are 9
or 10, I think. Yeah.
And then there's another class online that's just self-directed, Multiplication Explorers, and that has sparks. And we're working on, it's going to take a few months, 6 months more. We hope less than that, but we're working on an area on the site where all the sparks will come together from everything and all the books and everything she's worked on for 20 years. And that will be a membership area where you can get to everything. And have them in Spark format because it's so nice to just print the one little thing you need and try it out with your family. Because I don't know about you, but I got books and they don't come off the shelf as much as you'd like kind of thing. So we've had a lot of homeschoolers ask for that. Like, I just need something I can print and do. So we're hoping to meet that need. And then videos. So the part of the purpose of our classes too is we can grab video clips of Randy showing his awesome triangle. I guess we'll have to pay him royalties. And then that can be shown so families can see, oh, this is what I can do with this spark. This is where it can go. And they'll be inspired and get to watch, be the fly on the wall and watch it happen too. That'll all be in there. So anyway, awesome. Thank you all very much. Have a great Saturday.
Great. Bye all.
Okay. That was good feedback.
Cool. That was great. Yeah. No, thanks. This is, it was fun. I think we